All right, let's continue our discussion on matrix inverses. We'll try and finish the module today. Okay, so far we've looked at what are we know what are matrix inverses. Whenever we have a square non-singular matrix, that means full rank matrix, then there is an inverse. There is a unique inverse for that matrix, such that if you pre-multiply or post-multiply, you'll always get the identity matrix. And we said that the inverse actually corresponds to a basis change operation geometrically. Right? You can use A inverse to find the representation of a vector in a different basis. But which basis? What basis does A inverse allow you to convert to? Yeah. Well, the basis it corresponds to is the basis formed by the columns of A. Right. Now we'll move on to a couple of other important topics in matrix inverses, which is essentially the idea of left inverse and the right inverse. Okay. So it turns out that there are cases where you have a matrix A, and if you pre-multiply, you get the identity matrix. But if you post-multiply, you don't get the identity. Okay. Similarly, there are cases where you post-multiply and you get identity, and you pre-multiply and you don't get the identity matrix. Okay. So whenever this happens, right, you pre-multiply and you get the identity, then B is called left inverse. Okay. It's called left because B goes on the left of A. Okay. And in this case, where you post multiply and you get an inverse, here B is called the right inverse. We'll talk a little bit more about left and right inverses. It's just that when you have a square matrix that is full rank, the left inverse and the right inverse are the same. In fact, there is a left inverse and a right inverse, and both of them are the same whenever A is square and full rank. Okay, we'll first start with the idea of left inverses. And we can talk about the idea of a left inverse. I mean, we can talk about a pure left inverse or a right inverse only for rectangular matrices and full rank matrices. Okay, if the matrices are not full rank, they of course don't have a left or right inverse. There is no inverse. So being full rank is necessary for you to have an inverse. If it's square and full rank, left and right inverse exist. Both are same. That's simply the inverse of the matrix. If it's full rank and rectangular, either you'll have left inverses or right inverses, not the other one. Okay. So if you have a rectangular matrix that is tall, okay, like this. And now we are talking about matrices that are M cross N. We're not talking about N cross N matrices anymore. Okay. In this case, M is greater than N. If it's full rank, what is the rank of A? I'm going to call this the matrix A. What is the rank of A if I say it's full rank? N, yes. Smaller of the two. A will have a left inverse. Okay. Some matrix B such that if I multiply B and A, I will get I. But what shape will I be? IM or IN? Well, I should first say what the dimension of B is, or what the shape of B is. This is M cross N. If B is a left inverse of A, then B will have the shape N cross M. In this case, what will be the shape of I? N. It will be IN. Okay, that means you have the left inverse B multiplied by the original matrix A, then you get I. In fact, this is identity matrix, 0 below, 0 above. Okay. And see, now you could ask, well, if this is possible, if BA gives me I, why can't I have this IM, that this is M cross N, and this is N cross M. If you multiply these two, you will get a M cross M matrix. Now, you could ask, well, why is it that we can't, I mean, how do we know for sure that we can't get IM by post multiplying A by some matrix? We can make a geometric argument as to why that is. Okay. You have A, right? It's full rank. M cross N. M is greater than N. Okay. What space are the columns away from? Well, there are only two possibilities, Rm or Rn. What space are the columns away from? Yep. How many elements do columns away have? N or M? Okay. This M, right? There are M rows. That means there are M numbers in each column. That means the columns away are from Rm. Right? If you take the matrix, right, A, and post multiply it by anything, like post multiplied by a column vector or a matrix, right? What you're doing, I mean, let's say we take a matrix like this. B, this is N cross M, and then you're producing a M cross M matrix. Right? What can you say about the first column of this matrix? I'm going to call it A, B, call it D. What can you say about the first column of D? How is it related to A and B? Okay, the first column of D is a linear combination of the columns of A. The exact linear combination or mixture is given by the first column of B. The second column of D is again the linear combination of the columns of A, and the exact mixture is given by the second column of B, and so on and so forth. That means each column of D is a linear combination of the columns of A. Okay, there are only n. So here M is greater than n. That means the subspace spanned by the columns of A, that means the column space of A, is a proper subspace of Rm. It's a smaller dimensional subspace sitting in Rm, because the dimension of the column space of A is simply the rank of the matrix. The rank of the matrix here is n. That means the set of vectors that you can produce by the linear combination of the columns of A sit in an n-dimensional subspace within a higher dimensional vector space, that is Rm. Right? Now, if you want D to be equal to the identity matrix, right? So I'll add another point here. If you have a subspace that has dimension R, right, or even before that, when we talk about Rn, right, how many vectors can I take from Rn and form a set before the set is guaranteed to be linearly dependent? Yep, n. Right? There are only n possible vectors that I can take and still have a linearly independent set. That is for Rn. What if I have a R-dimensional subspace in Rn? How many possible vectors can I take from a R-dimensional subspace before the set of vectors remain beyond which the set is guaranteed to be linearly dependent? Well, if I have a one-dimensional subspace in Rn, how many vectors can I take from a one-dimensional subspace before the set is guaranteed to be linearly dependent? No. I can take one vector. If I don't take zero, for example, if you're talking about R2, this is the origin. So this is a one-dimensional subspace. Let's assume I'm not taking zero. I'm taking other vectors, non-zero vectors. I take one vector. This is some non-zero vector. A. Because this is non-zero, this set is linearly independent. So I can take one. Can I take one more? For example, can I take B and form a set A, B? Well, you can't because they're collinear. Okay. So when you have, so this is in a one-dimensional subspace, you can only take one vector before the set becomes linearly dependent. If you have a two-dimensional subspace, let's say a plane passing through the origin in R3, there are only two vectors that you can take from that subspace before the set becomes linearly dependent. Similarly, if you have an R-dimensional subspace, there are only R vectors that you can take and form a linearly independent set. Beyond that, you are guaranteed that the set, if you take one more vector and form the set, that set is guaranteed to be linearly dependent. Okay. So, coming back to this problem, the column space of A has a dimension n. Okay, that means we can only take n vectors and have the set to be linearly independent. Okay, the moment you take anything beyond n vectors, you're guaranteed to have a set that is linearly dependent. Okay? Now look at this. What if you look at the columns of I, right? Im. There are m columns, all unit vectors, m unit vectors. That means you have m linearly independent vectors there. Okay, because when you do AB, all the vectors you produce can only come from the subspace spanned by the columns of A. There is no way you can produce m linearly independent columns. You can only, at the max, you can only produce n linearly independent columns. But here, m is greater than n, so this is not possible. In fact, you cannot produce any matrix by doing AB such that the rank is greater than the rank of A. This is something we did not look at, but if you have a matrix A and a matrix B, they say this has rank R1, this has rank R2. You can ask what can we say about the rank of AB? Rank of AB cannot be greater than the smallest rank of the two matrices. Okay? Okay? That's why you cannot have this. IM is not possible. Okay? You can make a similar argument for the right inverse as well. Let's start with a very simple example. Okay? We're talking about left inverses. Left inverses exist only for tall matrices. Okay? The simplest possible tall matrix is what? Sorry. In terms of their shape, in terms of M and N. Sorry. You say, I won't hear. N cross 1, exactly. Just one column. N cross 1 is it? So the matrix is M cross N, sorry. Yeah. What is the simplest possible? Well, it's just one column. Okay. So let's ask, well, if I have a matrix A, there is just one column. Okay. Let's say C is the left inverse of A. If I multiply C by A, what will I get if C is the left inverse? Well, I'll get the identity matrix of size 1. That is simply the number 1. So whenever you have a single column, the left inverse of that column is such that when you multiply them, you get 1. Okay. And what will be the shape of C? This is M cross 1. What will be the shape of C now? 1 cross M. Okay. Let's do an example. We want to find a matrix C. We'll call it C1, C2, such that CA will give me I. In fact, this is equal to 1. How will you find out? Well, let's first multiply and see what we get, right? What will happen if you multiply C and A? It looks like in this case, the matrix multiplication is simply inner product. Okay? Means you get C1 plus 2C2 equals 1. How do we find C1 and C2? So essentially the question is what C1 and C2 will solve this equation. I am asking you, what do you think? Yeah? No? There is no other equation. This is the only thing. This is the only equation we have. Sorry? No. There is no other equation, man. Here, the question is this: if you have a matrix A, which is tall, is it full rank? The matrix A? Okay, all right. I'm just going to continue. Okay, matrix A is full rank because it's got one column and the column is not 0. So this is full rank. Rank is 1. Now the question is, how do we find a matrix C whose elements are C1 and C2 such that C times A gives me 1? Okay? And if you multiply C and A, you get this equation. That means any C1 and C2 that solves this equation can potentially be a left inverse of A. Right? For example, if I take C1 equals 1, C2 equals 0, then I get a matrix C equals 1. Sorry, it's a row. 1, 0. If I multiply 1, 0 by 1, 2, I'll get 1. Okay? So it looks like this matrix 1, 0 is a left inverse of A, or for this A. Okay? But is that the only possibility? Well, there are other possibilities, right? I can say 3 minus 1. I can say minus 2, 5. In fact, there are an infinite number of possibilities. That brings us to this concept, an important idea in when you're talking about left inverses and right inverses. There is no unique left. If there is a left inverse, there is no unique left inverse. There are infinitely many left inverses. And in fact, we'll also see for right inverses, there are infinitely many right inverses. So, in fact, if your matrix A had only one column, okay, any vector of this form, okay, you take the vector A, normalize it by its length, in fact, square it, okay, and of course take the transpose because it's a row, it's not a column. Okay. If you call this C into your matrix A will be 1 because C is A transpose divided by the square of the Euclidean norm. A is simply A. This is so A transpose A, inner product of A with itself, that's simply the square of the Euclidean norm. This will turn out to be 1. The numerator and denominator are the same. That's one possible left inverse. But if I add to this vector, right, any vector that is perpendicular to A, then if I do CA, I should still get 1. Okay? For example, let's say this vector is perpendicular to A. That means if you take the transpose of this, this will be equal to 0. Okay. So any vector of this form where some scalar will be a left inverse of A. Okay, because if you take C times A, in fact, I should point out I'm going to write it like this. Okay, will be A transpose square plus some alpha times B transpose multiplied by A. So this will be A transpose A square plus alpha times B transpose A. But B is perpendicular to A, right? That means this inner product will go to 0. Okay, and what is the numerator here? Well, the numerator is simply the square of the second norm. In fact, this is exactly what this applies to the previous example that we saw. What was A? A was 1, 2. Well, an immediate possible left inverse is you take square. Okay, so that would be 1, 2. What is the square of the length of A? Square of the length, that will be 5. Okay? That means this matrix 1 by 5, 2 by 5 is a left inverse. Okay, you can verify that. So if I take 1 by 5, 2 by 5 multiplied by 1, 2, I'll get 1 by 5 plus 4 by 5. Okay. Now, can you give me a vector that is orthogonal to A, perpendicular to A? Any vector. That means the inner product of that vector with A should give me 0. I'm going to call it B. Let's say B is perpendicular to A. Can you give me a B? Except B being 0. Don't give me 0, 0. Because that is perpendicular to everything. Yep. Yep. Minus 2, 1. Okay. Now, if I take this and I add simply B transpose. So some alpha times B transpose. Okay. What will I get? I know what is this. This is 1 by 5, 2 by 5. And this alpha times B transpose will be minus 2 alpha. So I will have 1 by 5 minus 2 alpha, 2 by 5 plus alpha. Okay. Any vector of this form is guaranteed. Any matrix of this form If I post multiply this matrix by A, I will get 1. You can verify later on that this is equal to 1. Well, let's just do it. By phi minus 2 alpha 2 by phi plus alpha or 1 plus 4. 1 by 5 plus 4 by 5 will be 5 by 5, which will be 1. So when you only have one column, this formula here will allow you to easily identify all the left inverses. But let's say now we generalize it to the general more complex rectangular matrix. That means it has more than one column. In that case, the matrix C, of course, will not be a row, but will have multiple rows. And if it's a left inverse, CA will produce I. And if you add, you can add to C any matrix C cap or C hat, and still get IM on the right hand side, as long as C cap plus A is 0, right? Because if you multiply this inside, C is a left inverse, CA will give me IM, and C cap A will give me 0, right? So if you can identify matrices C cap such that C cap into A is 0, then C plus C cap will also be a left inverse, and that's essentially what leads to infinitely many left inverses. Okay, because there are infinitely many C cap matrices such that C cap A gives me 0. Okay, let's do an example. Right, then it becomes clearer. Let's say my matrix A keep it simple. We want to find all the left inverses to this matrix. Okay, and we know the left inverse will be of what shape? This is 3 cross 2. What will be the shape of the left inverse? 2 cross 3, and I'm going to call them elements C11, C12, C13. Sorry, C21, C22, C23. Okay. And if I multiply these two, what should I get? If C is the left inverse of A, what would be on the right hand side? It has to be IN. N here is 2. That means it should be I2. What are the elements of I2? Identity matrix of size 2. Okay. Now the question is, how do we find out? Well, first let's just multiply the left hand side out, right? So you have you could say, well, see, hold on. We've seen how to solve Ax equals B. Now here is an equation where the unknown is a matrix by itself. Okay? If you look at it as matrices like this, then of course it's confusing. But if you multiply these two, right, you'll get 4 elements. in the unknowns, which we are saying is equal to the right hand side, which has 4 knowns. Okay? So it's essentially saying, so this solving for this equation is essentially solving for 6 unknowns in 4 equations. Right? The first equation would be the first element of, so if you multiply these two matrices, right? What will be the first element? Let's start from there. Sorry? Yeah, so it will be C11, the C12, the C13, and that is equal to, that means equating these two is the first equation. What was the second one? Third? Now maybe it's more clear. We have 4 equations and 6 unknowns. The equations are C11, the C12, C13 equals 1, C11 equals 0, C21, C22 plus C23 equals 0, C21 equals 1. That's all. This we know how to solve. Right? In fact, we know how to solve the full solution, particular solution and homogeneous solution. Yeah, I'll leave it now up to you to solve it and tell me, because you should know, I mean, you should know this by now. C23 equals, are you sure? Why? Yes. See, okay. What do we do? Here, you know how to do Ax equals B. Just do that. Get it to the reduced row echelon form. Then you know the rank of this system of equation. Then you know the dimension of the null space. That means you know how many uh, parameters you can take as free variables, and then you have the complete solution.